All right, so new section. I really like this section. I don't know why. Mainly because it's a little bit more intuitive than the other ones. I feel like limits are just like trying to trick you and make you think like you think you know what the answer is, but it's actually not. Continuity is a little bit different. Okay, so we're going to talk about continuity, which is like when you draw a graph, is it continuous? What's a basic definition of continuous? What do you think a basic definition would be, Michael?
Just all real numbers.
All right, okay, that is something that's continuous, but what about like how would I describe a graph being continuous? It's like a good definition for that, Sam.
There's no holes or breaks.
No holes or breaks, right? My definition, which is really simple, is you can draw it without picking up your pencil, right? So you can draw the graph without picking up your pencil. I don't know if that's good enough to write down, but draw without picking a pencil. Okay, and what we're going to do is we're going to look at some examples where things are discontinuous, and maybe through these examples we'll come up with a definition of if something's continuous or not. Okay, so I have a couple graphs here. The first one I'm going to draw, like Sam said, maybe a break, right? So how about this? Let's draw something that's discontinuous at the point A. So when x is a, we're going to have a discontinuity, okay? So let's say I have this function and it's going over here and we're going to have like a hole, okay? I'll call this hole L1. Okay, so at the height L1, we have a hole and then it jumps up at L2. So L2, we're going to jump up and our function has a little jump in it, okay? Now, pretty obviously, I took off my pencil to draw that. So I'm going to say that f of x is not continuous at x equals a. Okay, so this is the language that we use to describe this. And because we've been doing all this stuff with limits, let's just look at the limit and see what happens, okay? So let's see, we have the limit as x approaches a from the left of f of x. What's the limit as x approaches a from the left looking at the graph? L1, good. The function's at height L1 as we're going to the left. And from the right, we've got the limit as x approaches a plus of f of x. What's that limit? L2, good. L1 is different from L2, so the limit as x approaches a of f of x, does that exist? No, right? So this limit does not exist because the two limits from the left and the right were not equal, okay? So it's pretty obvious that if the limit of a function doesn't exist, we have discontinuity, right? So whenever that limit doesn't exist, not continuous. But this is not enough. Okay, so let me show you an example where the limit does exist, but we still have a discontinuity. Okay, let's still keep a. So we're still looking at that point A. And let's say we have a function, and maybe it's going down this time. Okay, and it's going down, but we have a hole. Okay, so at L, we've got a hole. Okay. This is also not continuous at A, so not continuous at A. Okay, sometimes we don't write x equals. It's just not continuous at A. Okay, now in this case, the limit does exist. What's the limit as x approaches A of this function? L, right? So the limit does exist. What's the problem here?
The actual value of a doesn't match the limit of it. Or
Okay, that is true, but the actual function doesn't even exist, right? So f of x, we're going to say f of x is not defined at a, right? F of a doesn't exist. There's no value of the function at a. Okay. So whenever we see a function and it doesn't have a value at a specific point, we're automatically discontinuous at that point. Okay, so limit doesn't exist, function doesn't exist. Both of those are examples of discontinuities. Okay, let's do one more example. I'll show you one where the limit exists and the function exists, but we're still discontinuous. Okay, so we're still going to be A. I'll keep L the same. I don't know if it's at the right point, but let's just keep it here. Let's say we have like the same function and at A we've got the whole, but the function is defined, but I'm going to define it up here. Okay. All right. Here, f of A exists, so we don't have that problem. So if I plug in A, we do have a value of the function. Another way of saying f of A exists means f is defined at A. Okay. We know that the limit exists. The limit as x approaches A of our function exists and it equals L, right? Okay. So why is my function not continuous? Michael? As a whole, right? And the problem is even though these two things exist, they don't match each other, right? Now, if the whole slid down and like match, like if the f of A slid down, it kind of like matched where the whole was, and of course the function would be defined at A, the limit would equal L, and the limit would equal where it defined, right? So this is still not continuous. I'm going to write discontinuous. Still discontinuous at A. I don't know if I spelled that right, by the way. Okay. The problem here in all three cases is what we needed for continuity was for the limit as x approaches A of our function, we really needed that to equal f of A. Okay. So the value of the function needs to equal the limit of the function if we have continuity. Okay, and that's the definition of continuity. Okay, we'll look at more examples, but let's just go to the mathematical definition of continuity. Okay, this is like the green box here is like the definition of continuity that if you're like a math major, you'll probably use in the future. We're continuous at x equals A if the limit of the function equals the function value at A. Okay, this definition is probably not very useful to you in this class, and this is why I have this thing called the continuity test. This is kind of the more important one that you'll be using and applying in our class. Okay, so this test says if we want to prove that f is continuous at x equals A, so we want to show that it's continuous, what we're going to do is first say that f of A is defined, right? We need that function to have a value at the point, or else it's like that second graph, and we don't like that. Second of all, we need the limit to actually exist, right? We can't have a jump. So maybe we need to check those one-sided limits to see if our function exists, okay? The last thing is we need the limit of our function to actually equal the function value, okay? So we need those two values from number 1 and number 2 to match, okay? This is something that I probably want you to like memorize, okay? Because you're going to need to go through these 3 steps to show me if something's continuous on a test or quiz, okay? Let's put this into practice. Here we have a function. In this example, we want to show, okay, we want to find out if our function is continuous or discontinuous at x equals 2. If it is, we're going to prove it using our continuity test. And if not, we're going to like explain why it's discontinuous, okay? Let's just go through the steps here. Okay, so step 1, f of A is defined. Is f of 2 defined?
Yes.
Yeah, right? What is f of 2? F of 2 is 5, good. Because it's 5 when x is greater than or equal to 2. We're good. Yes, f of 2 is defined. Okay. Number 2, let's find our limits. Now, one way you can do this is you can graph the function. I'm gonna find the limit. I'm gonna show you how to find the limit of a piecewise function without graphing it, okay? And I'm gonna set up a graph, but I'm not actually gonna graph it, okay, because I'm lazy. So let's say we have x equals 2. We know our piecewise function does something to the left of 2 and it does something to the right of 2. To the left of 2, what is it? Is it x squared or 5? X squared, right? So I'm just gonna write x squared here, okay? So let's pretend we have the graph of x squared to the left, and to the right we have 5, right? Okay. Let's do, if we want to find the limit, let's do left and right limits. So the limit as x approaches 2 from the left of our function, okay? Are we going to focus on x squared here, or are we going to focus on 5?
Squared.
X squared, right? Because we're going from the left. So instead of writing f of x, why don't I just write x squared, which is what we're looking for, right? Okay, what is the limit as x approaches 2, either from the left or the right of x squared? 4, right? You just plug it in. 2 squared is 4. Okay, so the limit as we go from the left of our function is 4. The limit as we go from the right of our function, well, now we're on the right side of our function. We're going to not focus on x squared anymore. Let's focus on the 5. This is the limit as we approach 2 from the right of 5. What's that limit? 5, good. Okay, we found our left and we found our right limits. What is the full limit of our function? Doesn't exist, right? When the limit from the left and the limit from the right are different, the limit doesn't exist. So we have DND. Okay, let's take a look at our continuity test. It says that the limit has to exist for something to be continuous. Is our function continuous or discontinuous at 2? Discontinuous, good. I just hear people saying dis. Discontinuous at 2. Okay, do I need to check my third part of the continuity test?
No.
No, right? Because I already found out that the function doesn't exhibit number 2, right? So I don't need to check number 3 because I already found that it disqualifies one of the parts of our continuity test. Okay, so don't check rule 3 if you've already found that the function is discontinuous. All right, any questions before we move on? Good. All right, let's go to example 2. I promise I'll let you on your own, but let me show you an example where we're proving something is continuous, going through all the steps. Okay, we have another piecewise function. Number 1, we want to find if it's discontinuous at 1. So let's see if f of 1 exists. What is f of 1? 1, because you're going to plug it into 2x minus 1, right? 2 times 1 minus 1 is 1. Okay, so f of 1 obviously exists, right? So we're good. Okay, so if you want to prove that something's continuous and passes number 1, this is all you have to write. Okay, number 2, I'm not going to graph the function, but let me just kind of sketch out what this function would look like if I did graph it. To the left, we have x, right? And when x is bigger than 1, we have 2x minus 1. Okay. Let's do the limit from the left. The limit as x approaches 1 from the left of our function. Well, let's see which value that would be. Am I going to focus on x or 2x minus 1? Going from the left. X, good. And what's that limit? 1, good. Just plugging 1 into x. All right. Let's go from the right. The limit as x approaches from the right of our function. We're not going to focus on x anymore. We're going to focus on 2x minus 1, right? Because that's on the right. Okay. Plugging 1 in, you're going to get 2 times 1 minus 1, which is 1. Good. Okay. Gosh, writing is so hard sometimes. What's the full limit?
1.
It's 1, good, because they match, right? And they're both 1, so the limit as x approaches 1 is 1. Okay, so it looks like we've satisfied number 2 of our continuity test because our limit exists. Oh, one thing I want to talk about, number 2, is I want this limit to exist and I also want it to be finite, okay? So if you want to go back to your continuity test, just say it's finite. What is finite? What does that mean?
It means that it has a limit to where it goes. It's not like infinity where it goes.
Good, right? Because when we find limits, yes, a limit cannot exist. Sometimes we say the limit is infinity or negative infinity as well. That wouldn't count for number 2. Okay, so if you find the limit and it's negative infinity or positive infinity, it doesn't check off number 2. Okay, so it has to be a finite limit as well. Okay. All right, let's check number 3. Step number 3 says we need the limit as x approaches a of f of x to equal f of a. Is that true? Yeah, right. The limit as x approaches 1 of f of x was 1. The f of that 1 was 1. So since part 1 and part 2 have the same answer, we also can check off number 3. Okay. So by the way, this means that our function is continuous at x equals 1. Okay. If you want to prove that something is continuous at x equals 1, you need to show these 3 steps. You need to show that f of 1 has a value. You need to find the left and right limits, or at least figure out that the limit is equal to 1. And you also need to state that your part 1 answer and your part 2 answer match. Those are the 3 things you need to show to prove that something is continuous at a point. Any questions on example 2? All right, if we flip our page over, we have another example. I want you to figure out if we're continuous. If so, I want you to prove it. If not, I want you to show the step where it doesn't work. All right, let's come back to the front. I'm looking around, we have some really good answers here. I picked on Tommy. I do want to talk a little bit about his notation, but you did a really good job showing your steps here. So do you kind of want to take us through your steps here?
Yeah.
Mhm.
I just said that at 0, it's 0,
Mhm.
and then I looked both sides of the limit, and they were all the same numbers, so.
Perfect. This would be fine for me. I think it clearly shows that you found the limit. Since all these numbers match, we're good. I do want to say, I think this would be fine, actually. I think some people were more detailed, and that's also fine. But I think this clearly shows it as well. Okay. Any questions on example 3? All right. All right, so if we go down, we can look at some more definitions. I know we love those. We talked about a function being continuous at a point A, for example, or point C. We can also be continuous on an interval, right? So maybe we're not interested if f is continuous at 2. Maybe we want to see if f is continuous on the real numbers, right? We want to see if it's continuous everywhere. Okay. Definition of continuity is pretty easy. A function is continuous on an interval or like the real numbers or something like that if it's continuous at every point in the real numbers. Okay. Now that gets kind of weird because you can't really you can't go through every point and see if f is continuous at every single point on the real numbers. That would take forever. But we'll talk about how to talk about continuity on an interval. Okay. We also have a theorem that's kind of important, but pretty obvious. If we have 2 continuous functions, then if we add them together, we're still continuous. If we multiply it by a constant, still continuous. If we multiply 2 continuous functions together, still continuous. And if we divide them together, we're still continuous, but just making sure that we also have to make sure that the denominator isn't 0 at any point, okay? All right, so we'll come back to that in a little bit. Few more theorems to go through. The first one, we're going to talk about different types of functions. We're going to see where they're continuous And instead of checking to see if the function's continuous at all these different points, maybe we can just say the function's continuous because it's this type of function, okay? So first of all, we have the constant function. And this theorem says that the constant function is continuous on the real numbers, which means it's continuous everywhere, okay? I do want to do a little proof of this because I think it's pretty easy to prove. And the way I'm going to do this is I have an example of a constant function, and this might give rise to how we go about this, okay? Okay, this example is the constant function where k equals 3. So you can kind of imagine this being f of x equals k instead of f of x equals 3, right? And instead of the function being height 3, you can think of it being height k, right? Okay, I want to show that this function is continuous at any single point. So instead of checking every single point on the number line, which would take forever, by the way, I'm just going to pick a random point, okay? I'm going to pick this one and call it C, okay? And it doesn't matter that I put it between 3 and 4. I could have put it next to 0 or at negative 1,000, okay? It doesn't matter. It's just any point random. I'm going to call it C, okay? I'm going to say C is a real number, okay? Well, we have a continuity test. Why don't we go through the test and see if it checks all the boxes, right? Number one, we have to see if our function is defined at C, right? What is f of C? Not quite. Look at the graph. What would our function value be at C? K, good, right? Because at C, our function's value is here, which is, I know it's at 3, but in general, it would be K. Okay, so f of C is K, right? We got the limit, and instead of doing left and right limits, I think we can figure it out pretty good on this graph. Let's do the limit as x approaches C of our function. Okay, what is the limit as x approaches C of our function, which is K? What is that limit? Three or K in general, right? Okay, so if we go from the left, our function's approaching K. If we go from the right, our function's also approaching K. So this limit is also going to be K, okay? All right, well, third thing, we have to see if number 1 and number 2 match. Do they match? Yep. The limit as x approaches C of K is K, and that is f of C, which is also K, all right? So since number 1 and number 2 match, we've matched all of these properties, which means that f is continuous at C, which represents any real number, right? F is continuous at any real number, C, okay? And since it's continuous at any point, using our definition of continuous on an interval, we know that f is continuous on the real numbers, okay? All right, I know some of you might not be math majors and not want to prove things, but I like to stick them in every once in a while. All right, any questions on theorem A? All right, scrolling down, we got theorem B. The identity function, f of x equals x, which is our diagonal line, that's also continuous on the real numbers. You can actually prove this is true using the same sort of method we did with theorem A, but we know that the identity function is also continuous. I'll also throw out another one. The polynomial functions are continuous on the real numbers, okay? If you want to prove theorem B and prove theorem C, see me in office hours if you want to try it. I think they're not too bad of the proofs, but if you ever want to do those, then let me know. All right, let's move on. We talked about some functions. We talked about the constant function. We talked about the identity function. We know polynomials are continuous on the real numbers. Let's talk about rational functions. What are rational functions? Polynomial or polynomial, right? These are poly over poly. Okay. I know that the numerator or the polynomial on top is continuous everywhere because we know that polynomials are continuous. We know the denominator is a polynomial, which is continuous. So the denominator is continuous everywhere. So we know from our theorem that we talked about before, if we divide two continuous functions, it's also going to be continuous, except where the denominator is 0 at C, right? Okay, so the answer to this question is rational functions are going to be continuous everywhere. Okay. Except when the denominator is 0, right? Except where our denominator or q of x equals 0. Okay. So we know that rational functions are going to be continuous, except where we got that denominator being 0. What if the denominator has no roots, which means q of x equals 0 doesn't have a solution? Where would our function be continuous then? It actually would be a lot of places. So let's say we have, let me give an example, 3x plus 1 over x squared plus 1. Here, my denominator doesn't have a root because if I solved x squared plus 1 equals 0, I wouldn't have an answer. It'd be imaginary, right? Where would this be continuous? Everywhere, right? So rational functions continuous everywhere except where the denominator equals 0. If there's no place where the denominator equals 0, we're continuous everywhere. Okay. All right, let's take a look at an example real quick. Not too bad here. We've got this function. I put a crazy polynomial up top, but it's still a polynomial. So don't worry about the symbols here. The denominator is x times x squared minus 81. Where is our function going to be continuous? Sam?
Everywhere but 0
Mhm.
and 9, -9.
Perfect. If you don't know where the 0, 9, and -9 came from, we're going to take the denominator, set it equal to 0, right? We have that thing called the zero factor theorem that says we can take each value or each multiplied factor, set it equal to 0, and solve for x. Okay, so x squared equals 81, x equals plus or minus the square root of 81, x equals plus or minus 9. Okay, so that's how we get those numbers. We know that 0, -9, and 9 make the denominator equal to 0. So this function is continuous everywhere except those x values that made the denominator equal to 0. So except 0, -9, and +9. Okay. Any questions so far? Yeah.
So is there holes at those points?
We're actually going to talk about what happens with rational functions. I would expect there not to be a hole at those points because the holes come apart when you factor the numerator. Yeah, and they cancel. So we'll talk about next class what happens when we have rational functions. Is it a hole? Is it an asymptote? What's going on? But I think what we'll do is we're actually going to save that for tomorrow because we have a quiz review to go over. But that's a really good question. All right. So I don't see anyone on Zoom. So let's go through the quiz review.